In section 6.4, we'll be discussing accumulation functions and the fundamental theorem of calculus. So the first thing we're going to discuss is finding net area. So whenever you see net, that really just means a change in something. So a change in area is what we're talking about here. So here's a graph of f, and we see it has two straight lines here, and then two quarter circles, one quarter circle here, one quarter circle here. And we are given a different function, g of x, which is defined to be an integral from 0 to x, f of t dt. It asks us to find some specific values of g. So what you need to keep in mind is that when we have a function, like g of x, that means if I want to find g of 0, for example, I would plug in 0 wherever there's an x. When I look at this integral, the x is on the integral itself. Notice these are t's here, so I'm not plugging it into the integral, I'm plugging it into the bound or the limit of the integral. So g of 0 means I integrate from 0 to 0, f of t dt. Now, don't let the variables mess you up. This is f of x, but f of t dt is just a dummy variable. As long as those variables match up, it doesn't actually matter what they are. And so if I integrate this function from 0 to 0, it's just 0. Remember, whenever those bounds are the same, my integral is 0. For g of 1, that means I'm going to integrate from 0 to 1. So I'm plugging in 1 to the x on my function, f of t dt. So from 0 to 1, I notice I have a triangle there, base 1, height 2, so that has an area of 1. I'm going to go ahead and label those areas on the graph as I go, so that will help me find some other integrals as well. G of 2 means I will integrate from 0 to 2, f of t dt. So now I'm going to add on this rectangle of area that has an area of 2. So I have 1 plus 2, which is 3. G of 4 means I'm going to integrate from 0 to 4, f of t dt. So now I'm going to add on this quarter circle. Remember, our area for a quarter circle is 1/4 pi times our radius squared. Our radius here is 2 from our center to the edge. So 1/4 of 4 pi is just pi. So I have 1 plus 2 plus pi, that's 3 plus pi. For g of 6 then, we're integrating from 0 to 6, f of t dt, which then means I'm going to have this area as well. Again, that's a quarter circle with radius 2, so that has area pi. But I'll have 1 plus 2 plus pi minus pi, so that will just give me an area of 3. So notice as I went, as my x's increased, I added area on each time, except for right here I subtracted it. But we're essentially adding these on, keeping in mind the signs. And so this is called an accumulation function because it accumulates area as x increases. So you've probably heard accumulation a lot, like snow accumulation. We add area on as time goes by, or add snow on as time goes by. Same idea with this area here. So that idea of an accumulation function leads us to the fundamental theorem of calculus. Now, when you see a word like fundamental, you should think it's very, very important. A fundamental theorem here, it just connects the two parts of calculus that we've been studying, derivatives and integrals. We'll talk more about the second one later, but let's go over one right now. We're assuming that f is continuous. If g of x is equal to the integral from a to x f of t dt, so that's one of these accumulation functions. I can tell it's an accumulation function because there's a variable on the integral. Then if I take the derivative of g, I get f of x. In other words, if I take the derivative of the left side and take the derivative of the right side, when I take the derivative of that integral, it essentially cancels out, and I would just have the f of x there. The second one says if I integrate a function from a to b, then that's equal to the antiderivative at b minus the antiderivative at a, where big F is any antiderivative of f. In other words, big F prime is equal to f. That might look confusing, but essentially what we're saying is if we integrate from a to b a derivative, then that is the underivative, we call it antiderivative, f of b minus f of a. We'll talk about that a little bit today, but we'll go over that one more in detail later. We're going to focus on number 1 right now. So we're going to use the same function that we were given above, which was g of x is equal to the integral from a to x of f of t dt. And we're going to use the fundamental theorem of calculus to help us here. So g prime of x just means I'm taking the derivative of this integral, which the fundamental theorem of calculus tells me is just f of x. So then when I want to find g prime of 1, that means I really just want to find f of 1. So I'm going to look back up at my graph of f. f of 1 is 2. So notice I'm looking at the y values on this graph because this is the graph of f. So f of 1 just means the y value on the graph of f at 1, which is 2. G prime of 4 means I will find f of 4. And again, I'm just going back. I've already said that g prime is equal to f. And so then if I want to find f of 4, or g prime of 4, that's just f of 4. So I look at the graph. f of 4 has a y value of 0. If I look back up at the graph, at 4 has a y value of 0. My last one is g prime of 6. G prime of 6 is going to be the same as f of 6, which I see here as negative 2. So that's f of 6. I saw on my graph that that was negative 2. Now we can do that same kind of function analysis that we did back in unit 3, 4, I think it was unit 4, with these functions. But you have to make sure that somewhere you say g prime is equal to f. So then when we're looking at this graph of f, we're also looking at the graph of g prime. So if I ask questions about g, what I'm given is g prime. So the first function, or the first question asks, on what intervals is g increasing? So remember that means that g prime is positive. So I'm going to look back up at my graph. I see that g prime is positive from 0 to 4. So I'm going to say g is increasing on 0 to 4 since, now I could say g prime here, but I'm going to say since f is positive because that's what the graph that I see. As long as I've stated this somewhere in my problem, I could use f or g prime here because I've already said they're the same. So either one would actually work right here. F asks where does g have a relative maximum? So remember that means where does g prime change from positive to negative? So I'm going to look back up at my graph of g prime, which is the same as the graph of f. Where does this graph change from positive to negative? I see that happens right here at 4. So I can say g has a relative max at x equals 4 since f changes from positive to negative. Part G asks on what interval is g concave up. So that means we're going to look to see where g prime is increasing. Let's look back up at the graph. G prime or f is increasing only on this piece right here. It's constant right after that and then decreasing. So from 0 to 1. So g is concave up on 0 to 1 since f is increasing. And once again, I'm just reiterating here that that graph of f was the same as g prime. So I could use either f or g prime here as long as I've given this equality. This statement is super, super important to give on a free response question. Now we're going to use the second part of the fundamental theorem of calculus. Something we'll go over more later, but we're using this as an idea of net change. And so we've already talked about this, like when we integrated velocity, it gave me my change in position. So that was one of the first things we talked about in Unit 6. And so you can think of it as if I integrate my velocity, it would give me my position at B minus my position at A. What we're going to do is kind of flip that formula around and say if I'm looking for some end amount, it's equal to my starting amount plus my net change, which is the integral of a derivative from a to b. Okay, so my end amount is equal to my starting amount plus my net change. So you could think like my ending position is equal to my starting position plus the integral of velocity, my change in position. So that's the change there that we're adding on. So for example, we're given a graph of f prime here, and f is defined as or on this interval from -4 to 4, and we only know this one point, f of 0 equals -3. That's the only point we know. Here's the graph of f prime, which is the derivative of f, and what we're going to do is try to work backwards to figure out what f of 3 and f of -4 are. Now we can't figure out the whole function f, but we do have this formula up here. And so what we want to find, f of 3, that is equal to, now this f of 0 equals -3. We want this to be our starting amount. So I'm given one amount, that's my starting amount, and then this is the amount that I'm trying to find, my ending amount. One thing I want you to notice on this formula is f of a, this right there, that value has to be my lower limit of my integral in order to use this formula. So notice that those are the same. The one I'm trying to find is my upper limit. So to find f of 3, I would do f of 0 plus my integral from 0 to 3, f prime of x dx. So f of 0, that was given to me, that's -3. This integral, 0 to 3, f prime of x dx, I can find from my graph. So I have this triangle here that has an area of 2, base 2, height 2 times 1/2. And then this little triangle here, which has an area of 1/2. So I have -3 plus 2 minus 1/2, or -3 plus 1.5. So that gives me an answer for f of 3 of -1.5. For f of -4, so again, the f of 0 is what I know. And so if I want to find f of -4, I'm going to add on the integral from 0 to -4, f prime of x dx. Now this might feel a little weird to you because usually we put the lower number on the bottom and the smaller number on the top. So I would encourage you to flip that around. But if I flip it around, remember that I have to switch the sign. So I'm going to subtract that area. So I have -3 minus whatever the area is from -4 to 0. Now this is one of those tricky problems for this area. So what I need to do is, I'm trying to find this area here. So I have to take this rectangle minus the semicircle that's here. I'm going to subtract that semicircle. So my rectangle is 4 times 2. Then I'm going to subtract my semicircle. I see that my semicircle has a radius of 2. You can either go down or across there. So 1/2 pi times 2 squared. So this will be 8 minus 2 pi. That's this area here. But because essentially I'm going backwards, I'm going from 0 to -4, I'm going to have to subtract that area. So I'm subtracting the 8 minus 2 pi. So then I have -3 minus 8, that's -11, and then minus a -2 pi. So -11 plus 2 pi there.